Hello, dear students. In this session, we are going to talk about the concept of game theory. Game theory, as the name says, is a game between two or more different sides of a war, of a politic, of a competition, and the strategies that they select about those decisions, and the final objective and the final purpose of this decision making is to win and try to increase as much as possible the chance of winning of that competition or that campaign or whatever that we'll see in the next slides. So, in this class, what we'll do, we start with a brief introduction to enter to the world of game theory. The second one, we apply some different methods and understand the formulation of the easiest form of the game theory, that is the formulation of games of two people or two players and zero-sum game. Third, we continue with games with mixed strategy. Then we focus on graphic solutions, and then we dedicate a little bit of time to solution through linear programming, and we conclude the concept and we close it. So this theory, this game theory, is based on mathematical solutions. Okay, we'll see it applies based on the type and the size of the example. It applies normal algebraic solution that we know this is a pure mathematic, or the graphic solution for the other type of examples. Okay, and finally the linear programming that we learned in last semester, the concept of linear programming. As I told you, the size of the example says which model we need to apply, that we'll see it in the next slide. It's very easy. And as I told you, in this session, in this class, we only focus on the concept of the two people zero-sum game. Okay, so although there are different applications of this game theory, such as in the war, such as in the campaigns of politicians, such as the football match, or different, okay, but in this case we are interested into concept of using game theory in business and economics that are more related to the concepts that we learn. But for sure, when we are talking about two people zero-sum game, we are talking about two competitors, two different competitors with different number of strategies. This different number of strategies shows what is the size of the example. Besides, it's important to mention that the concept of game theory is very, very important and very, very diverse, that economic scientists in 1994 and 2005 won the Nobel Prize for doing a research on this concept. So let's review a little bit when we are talking about the formulation of two-person zero-sum game, exactly what we are talking about. Okay, so when it says two-person, obviously there are two players doing a game, and zero-sum game is the amount won by one player is lost by the other players. Let's give you an example. I am playing with my friend, and based on the different strategies that I have and different strategies that my friend have, we decide a strategy, okay? And finally, I will win, for example, 2 units of value. When I am saying about 2 units of value, is something agreed between two sides, two players, okay? So it means, for example, when it's 2 units of value, it can be 2 cents, it can be €2, it can be $2 million, it can be 2 apples, it can be 2 whatever. Okay, guys? So this is not that important. What is that? This value is important, that one player, for example, wins 2 units, 3 units, 1 unit. Okay? So the other side of this definition, zero sum. So when one player wins 2 units of value, for sure the other player loses that 2 units. So 2 plus minus 2, it's equal to 0. For this reason, the sum is equal to 0. Better saying, when I'm playing with my friend, when my friend loses, he pays €2 to me. So he's minus 2 while I am plus 2. So 2 plus minus 2, it's equal to 0. Let's check a very simple example. Imagine I am playing with my friend with a game with name odds and events. Okay, I have 2 options while my friend has 2 options too, or showing 1 finger or showing 2 finger. Okay, at the same time we show our fingers. So what are the situations? Or when I show 1 finger and my friend shows 1 finger, I show 2 fingers, my friend shows 1 finger, I show 1 finger, my friend shows 2 fingers, and I show 2 fingers and my friend 2 fingers. Okay, so as you saw, there are different strategies. I have 2 strategies, 1 finger or 2 fingers, and my friend as well, 2 strategies, 1 finger or 2 fingers. Okay, the combination of these 2 strategies shows 4 different values for this type of game. If they match 1 finger, 1 finger, or 2 finger, 2 finger, I win 1 unit of value. If if they don't match 1, 2, or 2, 1, I will lose 1 unit of value. In the next slide, we'll see what we are talking about. So in this slide, just we are talking about 2% zero sum. What I win, my friend loses. What I lose, my friend wins. So exactly the value of these 2 items are equal. Okay, for this reason is zero sum game. To continue the concept of the last slide, let's focus on this slide. As you see, guys, this is the same topic that we were talking, the 2 strategies of odds and evens players. Okay, so as we reviewed, one player can have 2 strategies, or showing 1 finger or showing 2 finger, while exactly the other player has the same 2 strategies, one showing 1 finger and showing 2 fingers. Okay, for showing these 2 strategies of 2 sides, we use a concept, we name it payoff tables. Table, sorry. In Spanish, la tabla de los pagos. Okay? Payoff table shows payoff of player 1 if player 1 take even and the other. Based on what we learned, there are 4 different happenings. Okay? 1, 1, 1, 2, 2, 1, and 2, 2. Okay? There are 4 different happenings in this concept. Let's see what is the meaning of each of these items. Before reviewing this 1 minus 1 minus 1 and 1, okay, I tell you always the elements of this table are really easy. First of all, always the player 1 locates here, okay? And always the player 2 locates here, always. Never changes. When we are talking about two different players, we need to put them like this. As you see here, guys, we have the word strategy, okay? So this strategy can be different numbers, okay? Can be different numbers for the different players, player 1 or 2. In this case, you see player 1 has 2 and player 2 has 2 strategies. Do you remember? Showing one finger or showing two finger. One strategy or two strategy. Okay? While we have the same strategies for the player 2. So, what are these elements? As an example, what is the meaning of this -1? So we reviewed based on some agreements, if they don't be the same result, they are not evens, okay, as you see here, player 1 selects showing two fingers, while player 2 selects showing one finger. Based on the agreement, in this case, player 1 should pays one unit of value to player 2. For this reason, we show it with -1. Okay? One important item, guys. For for both of these two players, we only have this one table, payoff table, this one, okay, that reflects all information that we have. When this -1 says player 1 loses 1 unit, we can see it from the other side that for the player 2 is winning 1 unit. It's +1, okay, based on the concept of zero-sum game. Yes? So we just reviewed the payoff table of the previous example, odds and evens, okay? That we had two strategies for player 1 and two strategies for player 2. But always the number of strategies are not two. They can be more than two strategies. That in a general form for player 1, we show it with M number of strategies, M, and for player 2, we show it in a general form with N strategies. Okay, so the strategy determines to respond in each circumstance. Okay, so for each of the situation, for each of the circumstances, these strategies are the options of the players that can select for their game. And it is important to mention and remember that game theory is a rational game, okay, that both players think, both players try to win, okay, they need to choose strategies to win, or if they can't win, they try to minimize their loss, okay. So key assumptions, both players are rational, okay, so it means that two human bodies, it doesn't mean that I myself in front of the wall, okay, that can't think, I myself and the other player selecting a gold mine, for example, okay, I can think, but the gold mine can't think, okay. And in this case, as I told you, both of us, me and my friend, okay, one country and the other country, one supermarket and the other supermarket, one football team and the other football team. Both of them, they try to select some strategies to win that game. Okay? Now, after knowing a little bit about the different concepts of um, two-person zero-sum game, let's enter a little bit to try to solve the simple games by a prototype example. If you see, you can find it in your book, Hillier and Lieberman, this explanation completely, but we have the assumptions of this example here in this slide. What are the assumptions, sorry? Two politicians running against each other. So, what is the translation of these two politicians? Two players. Okay, so two-person until here. Both wants to campaign in big town and megalopolis. Whatever, they are two different cities that they want to make a campaign. What is the end? What is the value of that? Winning the number of votes, for sure. When one wins this number of votes, obviously the other one loses that number of votes. Okay, so for this reason is a zero-sum game. Let's review the other assumption. Both wants to travel at night and spend either one full day in each city or 2 full days in one city. It's talking about the different strategies that in the next slide we review them more comprehensively. And neither politicians will learn the other's strategy in advance. Okay, this is a fair game. Okay, this is a fair game. None of them knows about the strategies of the other one. Okay, so based on the different strategies, the result may have a winning for each of them or losing for each of them. We'll see in the next slides. In this slide, we try to review the different possible strategies for each of these two players, these two politicians, okay? As you see, guys, there are 3 different strategies for each of these politicians. So the size of the game is 3 by 3. 3 strategies for player 1 and 3 strategies for player 2. What are these strategies? Spend 1 day in each city. Spend 2 days in big town and spend 2 days in megalopolis. Okay? And based on selection of these strategies for each of these players, finally we'll see what is the value of the table. What is the meaning of this? The value of the table is the amount, is the unit that one wins and the other one loses. That, as I told you, they are equal and one is positive and the other one is negative. If it's a 5 winning of one player, it is losing the 5 units. 5 plus minus 5 is 0. For this reason, is a zero-sum game. One important item, as you saw here, the M that I told you, the size of the strategies, the number of the strategies of the player 1 is 3, while the N, the number of strategies of player 2 as well, is equal to 3. So M multiplied by N is equal to 3 multiplied by 3. While in the other example of odds and evens, the size were 2 multiplied by 2. 2 strategies and 2 strategies. It was 2 multiplied by 2. So when we are talking about the size of payoff table or size of the example, we are talking about these elements. In the next slide, we advance a little bit more in these concepts. As you remember the explanation of payoff table, after knowing the strategies of two players, these three strategies for each of them, the next step is forming the payoff table for this example. As you remember, as I told you, always the player one will sit here and the player two sits here in this part. Here is the list of the number of the strategies of player one, and here is the number of the list of strategy, the player two, the strategies of player two. As you remember, all the elements that enter here, all these 9 elements that enter here in this part are the units of value. They have the units of value, okay? And as I told you, based on the agreement between two players can have a unit, a dollar, a number of something, apples, I don't know, number of cows, whatever, okay? In this example, the entries are in thousands of total net votes. What is the meaning? I will give you an example. Imagine, for example, in this part, the strategy 2 for politician 2 and the strategy 2 for the politician 2 is 1 unit, for example. What is the meaning of that? It means that politician 1 or player 1 wins 1 unit of value, as here we have 1000 of votes, while player 2 loses that 1000 of votes. For this reason is a zero-sum game. And remember, we only have one payoff table. For this reason, when in this table, for example, we have 1, if we imagine the table of the other one is -1 in this place. Okay, guys? So, now let's review this table after obtaining the different results of the strategies for both players. Okay? As you see, guys, here we have a table with 9 different values that obtained for the strategies of each of these players. As you see here, for example, this number 4, that means player 1 selects strategy 1 while player 2 selects strategy 4. Okay? Strategy 3, sorry. Player 1 strategy 1 and player 2 strategy 3. So what is the meaning of number 4? The meaning of number 4 says player 1 wins 4,000 votes and player 2 by selecting strategy 3 loses 4,000 votes. So 4,000 plus minus 4,000 is equal to 0. Okay? So what is the meaning of this -1? Easy. It means that player 1 by selecting strategy 3 will lose 1,000 unit of votes. And what is the result for player 2 while selecting strategy 3? Easy. It means that player 2 wins 1,000 votes in this campaign. As you see here, this -1 for player 2 means a good result because it shows, because we have only one payoff table, this -1 for player 1 is losing, for player 2 is winning. And those zeros, the strategy 3 of player 1 and strategy 1 of player 2, and the strategy 2 for player 1 and the strategy 2 for player 2, it means that none of them wins or lose anything. Okay, so as you see here, guys, we have 9 different results, but which one will be the final result? Which one will be the value of our table? We'll see by applying some steps. Finally, we find the pure strategy. When we are talking about a pure strategy, it means that, for example, the strategy 3 of player 1 and strategy 2 of player 2. Okay, it is a possible solution. Okay, what I told you, based on the different steps, we'll find this pure strategy. And one more item, when I separate pure strategy, because the other side we have a mixed strategy. Just I will give you a brief explanation here in the next slide. Comprehensively we talk about that. A mixed strategy, it means that by a probability we select one strategy, and with another probability we select the other strategy, and obviously the sum of the probabilities is equal to 1. But at this moment, just focus on the pure strategy, and let's go to the next slide. Before entering to the next slide, let's review different elements of this table and different solutions that we can obtain for our table. So, as you see, guys, the size of this table, as I told you, is a table of 3 by 3. Okay, as you remember, in a general form, I told you the table has m multiplied by n. That while m is the number of strategies for player 1 and n is the strategies for player 2. Okay, so we can classify our results to 3 different groups, or like the odds and we have an example of 2 multiplied by 2. So in this case, as I told you, we can apply an algebraic solution that we see in the next slides. Or the size of the table is 2 multiplied by n, or m multiplied by 2. What is the meaning of this? It means that at least one side of the strategies is 2, the size of that. For example, or the player 1 has 2 strategies, or the player 2 has 2 strategies. In this case, as we reviewed before, we can apply a graphic solution. Okay, and finally, imagine a size of the table m multiplied by n. Based on what we reviewed in the other 2 groups of before, it means that the number of m and n in this classification should be 3 or more. Okay, although we can name it generally m and m, the size of the table, but in this classification, after 2 multiplied by n and m multiplied by 2, m multiplied by n means the size of table, at least each of them equal to 3 or more. And the solution of this size of table is linear programming. Okay, so what happens? There is a solution and there is a technique. We name it dominant strategy, that we see in the next slides. What is the meaning of this dominant strategies? Dominant strategy is a strategy that is better than the other strategy that convinces us to delete that worse strategy. Okay? What is the function of this? Imagine in this example, we have a table of 3 multiplied by 3 strategies, okay? Based on what we had, this is this type of m multiplied by n. And I need to apply a linear programming, the simplex and the other items. But by dominant strategy, I try to reduce the size of the table optimistically and ideally toward 2 multiplied by 2. But if it's possible to just change it to 2 multiplied by n or m multiplied by 2 as well, is a better and easier and faster solution than linear programming. So the easiest form is algebraic, okay, algebraic solution is the algebraic solution, and then graphic solution, and finally linear programming. So our try is try to reduce the size of the table to move toward this 2 multiplied by 2 size of the table. So let's see what are these dominant strategies. As you remember, I told you we have only one payoff table, okay, that reflects the strategies of both two players. For example, when we are talking about this element 4, this 4 means that player 1 wins 4 units by selecting strategy 1, okay? And player 2 by selecting strategy 3 loses 4 units of the value, okay? So for sure, in comparison between these 2 and 4, okay, for player 2, strategy 2 is better for player 2. Why? Because player 2 loses 2 units by selecting strategy 2, while selecting strategy 3 results losing 4 units. Okay, so in a general form, this 2 is better for 4 units. Let's make a comparison between strategy 1 and strategy 3 of player 1. So as you know, player 1 is a side that is a positive side. It means that more positive, better for it. Let's make a comparison between these 3 elements one by one. As you see here, guys, let's make a comparison between 1 and 0. Which one is better for player 1? Is 1. Why? Because it says player 1 by selecting strategy 1 wins 1 unit, while by selecting strategy 3, the player 1 wins nothing. By selecting strategy 1, if the player 2 selects strategy 2, player 1 wins 2 units, while by selecting strategy 3 by player 1 and strategy 2 by player 2, it wins only 1 unit. So again, strategy 1 gives him a better benefit. The same item is valid for strategy 1 and 3, while player 2 selects strategy 3, 4 and -1. So as you see guys, strategy 1 for player 1 is a dominant strategy, and I can delete the strategy 3 for player 1. Let's see what happens. P1 and P2. It means that is 1, 1, 2, 0, 4, 5. Let's review. If all the elements of one strategy, okay, are better than the other strategy, we can delete that worse strategy, like we deleted the strategy 3 for player 1. What just happened? As you see here, now we have a size of table 2 multiplied by n. Okay, 2 multiplied by n. What just happened? Instead of applying linear programming, I can solve this example with graphic solution that is easier for me. Now, I need to find another dominant strategies. Before going forward, I tell you guys, if you find dominant strategy from player 2 or player 1, there is no any priority. You can find whatever from wherever you want, from player 2 or from player 1. We started with player 1, and now at this point I want to find if there is any dominant strategy for player 1, for example. If not, I will go to player 2, but I insist there is no priority. You can start and continue with whatever player. For sure, the result will be the same. Let's review, guys. The elements of strategy 1 and strategy 2 for player 1 and 2. Okay? 1 is equal to 1. Okay, it's possible because when we are talking about dominant strategy is equal or more than that. At this moment, it's possible. Strategy 1 could be better than strategy 2. Let's review the other items. 2 is better than 0. Yes, because strategy 1, player 1 wants to win and be more positive. So 2 is better for it. Up to here, I can say that it's a dominant strategy. But for the comparison of strategy 1 and 2, what happens while the player 2 selects strategy 3? As you see here, the benefit of the strategy 2 here is bigger. So because of just this element, the strategy 1 can't be a dominant strategy in comparison with the second one, or vice versa. Here I don't have no more dominant strategies. But let's review from the point of view of the player 2. As you know, and as we discussed before, for player 2, it's ideal to have the less positive elements or more negative elements. For example, it means when it's -5, it means that player 2 wins 5 units. Okay, so for this reason, Those that are more positive, that are the strategies that we can try to eliminate them. So make a comparison between the elements now in the columns. Why? Because we are trying to review the strategies of player 2. Make a comparison between strategy 1 and strategy 3. So strategy 1, the value 1, while player 1 selects strategy 1, means that player 2 only loses 1 unit, but by selecting strategy 4, it loses 4 units. I'm talking about these two elements, okay? So which one is better? The strategy 1, because it only loses 1 unit in comparison with 4 units. Again, while player 1 selects strategy 2, player 2 can select strategy 1 or 2 or 3, but we want to make a decision between 1 and 3 to eliminate one of them. By selecting strategy 1, the player 2 only loses 1 unit, but by selecting strategy 2, it loses 5 units. So which strategy is dominant? Which strategy is better? The strategy 1. So which strategy can I eliminate? Strategy 3. Okay, so what happens? The size of the table changes to 2 multiplied by 2. Okay, that is 1 1 2 0. Okay, so this explanation was about the concept of dominant strategies that will help us a lot to simplify the table and minimize the type of the size of the table. In the next slide, we review some concepts of them. So this table that we have, this 2 multiplied by 2 table, okay, is a table that we can find if there is a dominant strategies. For example, as you see here, the first strategy is a dominant strategy than the second one. So I can delete this strategy and it remains 1 multiplied by 2. And finally, in comparison between these two elements, 1 and 2, in comparison between this strategy and this strategy for player 2, this one will be the result. Okay, that means both players 1 and 2 should select strategy 1, and it means that strategy the player 1 wins 1 unit while player 2 loses 1 unit. Okay, so in the next slide, we talk more about this concept and the solutions. So, in this slide, we just review what I gave you and what I told you in the previous slide. Here is just talking about the dominated strategies. Okay, as you remember, for player 1, the strategy 1 is dominant in comparison with the strategy 3. Why? Because all the elements of strategy 1 was giving a better profit than strategy 3. For this reason, we can eliminate strategy 3, and the size of the table from 3 by 3 changes to 2 by 3. I repeat, when it says better than the other one, it means that equal or more. And from the other point of view, the better strategy for player 2 is equal or less than. Why less than? Less than means less loss. Okay, less loss means more profit for the player 2. Based on these two comparisons, we try to eliminate the strategies by using this strategy, by using this dominant strategy. As you see here, after eliminating strategy 3 for player 1, what it remains for us is this table, this new table. Okay? Again, continuing with dominant strategies, this time for player 2, as we reviewed before, as you see here, strategy 3 is a worse strategy in comparison with 1. So strategy 3 is dominated by both 1 and 2. Okay? Although we make the comparison between 1 and 3, but 1 and 2, both of them are better than 3. So we can reduce and we can eliminate this column that we had before. Imagine we had a column before. Imagine we had a column before that now it doesn't exist. So the size of the table this time converts to 2 by 2 instead of 2 by 3. So strategy 2 becomes dominated by strategy 1 for player 1 at this point. Yes, a comparison between these two strategies, as you see. These two strategies, this one and this one. As you see here, all the elements of strategy 1 for player 1 are better than the elements for strategy 2 of the player 1. So strategy 2 should be eliminated. Finally, as we saw in the previous slides, okay, we remain with a table, something like this, okay? So again, by applying dominant strategies, because here we only have one strategy for player 1 and 2 strategies for player 2. But we want to know which strategy should player 2 select, okay? Again, in this point, the option is better for us that is smaller because means less loss, okay? In comparison between 1 and 2, which one is smaller? The 1. So the 1 dominates the strategy 2. So I can write both players should select a strategy 1 of each of them. So player 1 wins. Sorry. Wins 1 unit and P2 loses 1 unit. Okay, guys. As you saw, I told you both of them are rational and both of them try to win, okay, the units. So, but maybe you may ask me, but why player 2 loses? Okay, for sure. Always in this game, there is one winner, there is one loser. But by selecting and changing the strategy, if there is a loser, the loser wants to lose less than the other situation, like this part that I did. The strategy 1 selected by player 2. Why? Because he or she prefers to lose 1 unit instead of 2 units. Okay, let's go to the next one. The new variation, the new type of the examples that we see them in our examples is the variation that there is no dominated strategy. It means that from point of view the player 1, there is not one strategy, all elements of that better than the all elements of the other strategy. And from the point of view of a player 2, there is no strategy, all elements better, in this case less than the other strategy. Like this example, like this table 15.4, as you see, you can check, but there isn't any dominate strategy from different point of view. As you see here, for example, player 1, okay, has strategy 1, for example. Let's compare it with strategy 2. Strategy 2, while player 2 selects strategy 1 is better than 1. Strategy 2, 1 player 2 selects strategy 2 is better than 1, but strategy 2 of player 1 while player 2 selects strategy 3 is less than, because 2 is less than 6. Okay, and from the other side we have the same for a comparison of player 2, the strategies of player 2, as you see here. For example, -3 is better than -2, but 2 is worse than 0, while 5 is worse than -2. So all the elements are not dominant than the other one. If you check, there isn't any dominated strategy. So what should we do? How we select which of these 9 points? When we are talking 9 points, we are talking about the coincidence of the strategy of player 1 and strategy of player 2. Okay, which point of these two elements, these two players, is the ideal point? As you saw, we had one, for the previous one we had strategy 1 and 1, but in this case what should we do, guys? It's very easy. To this end, we need to calculate some elements. This solution, we name it minimax. Okay, what is the meaning of minimax? The minimax says each of the both players try to minimize their maximum of their losses. Okay, so to this end, for each of the players, we need to calculate 2 column and row. How? Imagine we have this table here. Okay, this 3 multiplied by 3 table. Easily we add this additional column and this additional row. For the player 1, we need to calculate the minimum elements of each of these strategies. Between -3, -2, and 6, -3 is the minimum element. Between 2, 0, and 2, 0 is the minimum element. And between 5 minus 2 and minus 4. Minus 4 is the minimum element. But from the point of view of the player 2 as well, happens the same item here because it's the different side of the table as we talked. We are talking here, we want to minimize the losses, okay? For the elements of each of the column, we need to find this maximum, okay? The other side was minimum. Here is maximum of each of the column. So we need to calculate this row 5, 0, and 6. How we calculate them? Easily. Between minus 3, 2, and 5, which one is maximum? 5. Between minus 2, 0, and minus 2, which one is the maximum? 0. Between 6, 2, and minus 4, which one is the maximum? 6. So now we have two new columns, a column of strategies of sorry, player 1 and a column and a row of the strategies of player 2. So between the column of minimums for strategy 1, we find the maximum value. A maximum value among minus 3, 0, and minus 4 is 0, okay? And in the row of the player 2, we need to find the minimum of the maximums, minimax of the values for player 2 between 5, 0, and 6 is 0. Okay? So, if there is a point, that this minimax and maximin happens is in the same coincidence, like here that we have 0, we name this 0 point as saddle point. That this saddle point means there is a pure strategy of strategy 2 of player 1 and the strategy 2 of player 2 is the point of the solution and the value of table is 0. It means that by selecting a strategy 2 of player 1 and a strategy 2 of player 2, none of them wins or loses, okay? The value of table is 0. This is the saddle point, in Spanish, punto silla. Okay, guys? This is the second variation, although there isn't any dominated strategies, but with these short calculations, we could find this saddle point to understand what is the result. Let's go to the next slide. In this slide, we have the same explanations that I gave you comprehensively in the previous slide, okay? Just review them rapidly. Minimax criterion that I told you, players select moves to minimize the maximum losses, okay? They want to minimize the losses when the resulting choices cannot be exploited by opponent to improve his position, okay? So both opponents are happy with the position. Player 1 should select a strategy whose minimum payoff is the largest, okay, for sure, because there are two different points of view, and player 2 should select a strategy whose maximum payoff the player is the smallest. So just again review the concepts. If this maximin and minimax happens in the same point of strategies, means coincidence, that for example in our example we had 0 while it was strategy 2 and 2, and this 0 strategy 2 and 2, this is the same point. We name this point, as you remember, as a saddle point that represents a stable solution. We name it equilibrium solution. So the result is strategy 2 and strategy 2 for both players 1 and 2. So in the variation tree, we review a situation that we don't have a saddle point. Okay, as you see here, by calculating maximin and minimax, the solution, imagine here, the optimal solution for player 2 here is -2. That means happening strategy 2 for player 2 and strategy 1 for player 1. So, but the optimal solution for player 1 is selecting a strategy 1 while player 2 selects a strategy 3. For the maximum value, let's interpret it what happens. This -2 means that player 1 loses 2 units while player 2 wins 2 units. So this result doesn't satisfy player 1. So the player 1 wants to have another type of solution. So he or she changes his or her strategy. So let's review the minimax value. This 2 means player 1 wins 2 units while player 2 loses 2 units. In this case as well, player 2 is not satisfied, so the player changes the strategy. So this changing will continue up to infinite. For this reason, we say that this type of variation doesn't have any stable solution. That is an unstable solution. Okay, so to this end and with this introduction, we enter to the next part, that is talking about the mixed strategies. As you remember, before we had a pure strategy. What was the pure strategy? Like a saddle point, strategy 2 and 2, strategy 1 and 3, just 1 point, okay? But mixed strategy, as I told you in the previous slides, is talking about the situation that with a probability, one solution, one strategy, and with another probability, another strategy. The combination of these, for example, 2 divided by 3 and 1 divided by 3, these are two variabilities. And for sure, always, sorry, probabilities. And always the total of these probabilities is equal to 1. Let's go to the next slide. In variation 3, we talked about the situation that there is not a saddle point. We named it an unstable solution. It means that there is not a pure strategy that says, for example, strategy 2 of player 1 and strategy 3 of player 2 is the pure strategy. When there is not this saddle point, we should solve our examples by a mixed strategy. A mixed strategy is the probability distribution of the different strategies. Okay, so when we have, for example, 3 strategies or 4 strategies for player 1, we should name each of these probabilities as x1, for example, x2, x3, and x4. And when we have, for example, 5 strategies for player 2, the probabilities related to these strategies is y1, y2, y3, y4, and y5. The coincidence, the point of this coincidence of each of these probabilities is the payoff of that table. That, for example, when we say the coincidence of the probability 2 of the strategy 2 of the player 1 and strategy 3 of the player 2, it's P2, 3. It's the element of the payoff of that two probabilities. So we need to write the expected payoff of that two probabilities that in the next slide I will explain it comprehensively. So to clarify what I told you in previous slides, in the mixed strategies, there are probabilities for the player one, xi, okay, that the probability the player one will use strategies from 1 to m. M is the final number that we show the number of strategies for player one, and the strategies yj for the player 2, that is j from 1 to n. For example, here in this case, there are two strategies for player 1, that is x1 and x2, while there are three strategies for player 2, y1, y2, and y3. Okay, as you see, guys, these elements that we have here, 5, -1, 0, and 2, are the payoffs. For example, this 5 is this Pij that we have here. All of them are this Pij. For example, this 5 is P12, and the combination of these elements, okay, with the payoff forms this formula, okay, that is expected payoff for player one for all these elements, okay, for all these four elements as an example in this table of payoff. To continue the last slide and to add to that, this expected payoff is the average payoff after playing many times the game, okay? So if we calculate this one, for example, as 2.5, okay, it's the average of playing many times the game. From the other side, minimax criterion for games lacking a saddle point, players should select the mixed strategy that minimizes the maximum expected loss to himself. Okay, exactly the same item that we had before for the minimax theorem, minimax criteria.